The goal of this project was to add a human flight controller to close the loop with feedback for motion control. This builds on the UAV's existing feedback control system, but in this case the human is the state observer of the plant outputs. The human's control inputs must be captured with the EEG, filtered with signal processing, and then finally transmitted to the UAV and injected into the normal UAV control system.
Electroencephalograms, or EEG, analyze brain activity by measuring scalp voltages using electrodes placed about the head. Previous work indicated that the primary motor cortex is an easily identifiable brain signal by EEG, and because either side of the body is controlled by only one side of the brain, relative activity between both sides could be used as the raw signal that will be processed into a command signal. The EEG data was processed using the method shown in the top right graphic. The data was filtered using a bandpass filter with a stop band frequency of 7.5 and 12.5 Hz and a pass band frequency of 9 and 11. Then it was passed into a MATLAB function block that saves the previous 100 values and then calculates the statistical inner fences. Those are calculated by taking the inner quartile range and multiplying it by 1.5. And from there, you add that value to the 75th percentile and subtract it from the 25th. If it doesn't fit within those fences, the data is rejected as an outlier. Rejecting meaning passing through the previous value. From there, the data is squared, and the data from the C4 electrode is subtracted from the C3 electrode, and then normalized to the average power of both of those electrodes. From there, a moving average filter is taken to remove overlying noise, and it's passed into the thresholding system.
To transmit data from Simulink to the UAV in real time, we use TCP/IP. This protocol indicates whether or not the signal has been received, so it is very useful for signal reconstruction. In the case where the signal has not been received, the TCP/IP block status port will output a 0, and this allows an enabled subsystem to hold the value of the previous signal, and this allows for the simple reconstruction of the signal. In some cases, there were signal errors that were not indicated by the status port. In this case, the values were close to 0 but not equal to 0. To fix this, we added a bias of 20, which then amplified all the error. We then filtered out any value less than 8 and then subtracted 20 to reconstruct the signal. This proved to work very well for all types of inputs, including sine waves and square waves.
To determine thresholds, we took several trials using different movements, where we processed the data in the way described. The trials were done by doing back-to-back movements on either side. It's important that both movements within each trial are done temporally close together because the signal is prone to slow drifting. For each dataset, we fit the data to a normal distribution, where we minimize the mean of the cost function to the top right. This cost function essentially maximizes the probability that the correct signal will be passed in, placing less value in minimizing the cost of indeterminate signals. The signal works by indicating right movement if the right threshold is surpassed in the positive direction, and indicating left movement if the left threshold is surpassed in the negative direction. This is because the positive direction means that the left side of the brain, or the C3 electrode, is more active, and the left side of the brain is well known to connect to the right side of the body. Indeterminate signals will cause the drone to hover, although this is unlikely to happen, as you can see from the graphs of the normal distributions on the bottom left. The actual thresholds have the constraint that they have to be set using the same z-score across all trials that we took, with the same movements, so that the thresholds will translate to other trials. The graphs to the bottom left show the examples of the data from different movements we considered. On the top is the fitted normal distribution, and on the bottom is the time series. The A column uses imagined arm movements, and the B column uses toe movements. The C column uses physical arm movements. We chose A because it gave the best odds of detection, as you can see from how well separated the means are and the low variance. This is most likely because movement will often add artifact to the signal, so the imagined movements will still produce waves within the primary motor cortex, but won't add artifact to the EEG signal. More data was taken later to determine the effectiveness of the signal.
The probability graph on the right gives the probabilities of the 3 possible outcomes: a correct command, an indeterminate command, and an incorrect command. As shown by the average probabilities on the bottom of the screen, a correct command will be achieved 66% of the time, which means that over time the UAV will move in the chosen direction. Because of issues with Simulink crashing during live streaming due to the LSL inlet failing, the control inputs were not done in real time. In addition, the EEG data transmitter began to crash the data streaming software right before the final test flight was about to take place. To get around this, we use data from one of the trials, and the commands over time are shown on the left side. This data was fed into Simulink from the MATLAB workspace instead of being fed into real-time through the LSL inlet block. The following video shows this resulting test flight. In this test flight video, first the UAV will take off and hover for a few seconds before it begins to receive the TCP/IP signal. It will then move to the right slowly because it's not a constant signal due to some indeterminate readings. It will then start to move left at a constant speed until it stops and moves right slightly. And then it will move left again, first slowly but then at a constant speed once it receives a positive signal, and then it will land.
As it is now, this method is far from perfect. Future methods can involve seeking types of adaptive thresholding to reduce the adverse effects of reliability that are caused by the drift of the final unthresholded signal, as well as further methods of increasing the signal-to-noise ratio.